Okay. Let me see. So we are like almost everyone, I think. Check this. Just give me a second. Okay, so we are. Okay, I think we can start the course. We need to go through some logistics before we start the course. So let me see this thing. Just give me 1 second. I need to download some things. Okay. Yeah, I have already shared with you the lecture notes for today. Okay. Okay, let's go to the slides. Awesome. Awesome. So this is the excellent, Mauricio. Okay, so this is the logistic. Let me see. As you probably know, we will communicate each other using my email. Okay, my email address is that one. It's jm.ramirezc@the-rest. The classes are going to be on Wednesday and Fridays from 7:30 to 9:20, and on Saturdays, as today, from 9:30 to 11:20. Okay, before I had the rooms, but now the room can be any place, your house now. Also, I want to know, you need to agree about which day we can use to have a makeup class if I'm not able to assist to a class, so we can coordinate a makeup class. Probably it could be on Saturday. You just let me know. You have to agree among you and let me know. Okay. The course website will be Blackboard and Blackboard Collaborate Ultra. And as you know already, because you already know the TA, Gonzalo, the software what we will use will be R and RStudio, right? R is a very powerful tool for statistical analysis and for econometrics. One of the most important features of this program, and that make it very appealing, is probably the fact that it is open source, so you don't need to pay any license. You can use it without paying anything, and there is a huge community that contributes to increase all the capabilities of uh, this program. Okay. So I have this academic integrity. Those are and this request for correcting a grade. Those are some of the rules that you have to stick with if you need to. Those are talks about that you should talks about the plagiarism, cheating, and the way you have to. I think the last one doesn't work now. Yeah. Anyways, let's go to the next slide. These are the references for the course. Probably I need to add some others references. Most of the things that I will evaluate in this course will be in this. Okay, so don't worry about that. If you need something else, I will post it in the Blackboard. Okay, don't worry about that. And if you need more information, just let me know. If you need like, some other stuff to learn the things that I'll be you, just let me know. Okay, I will be very, very, very pleased to help you. So of the course, the objective of the course is learn several quantitative tools for time series analysis. You will learn, probably the most important part of the course is implement using R for taxes, for forecasting, for risk modeling, and hopefully for optimal asset allocation. So all of these tools that you learn will help you not only for your work, all when uh, you are during the job search, have a nice conversation with the interviewers, with the people that want to hire you. Sometimes it's very, very interesting to have a talk where you can show off of the things that you know about uh, quantitative finance. Okay, for example, if I'm interviewing someone and this guy tell me things like, okay, during the university I have in some projects I have learned how to use R to forecast in the markets. I know how to use R to construct photos. Uh, these are the kind of things that like engage the conversation, can like make the difference between you and other candidates during your research. So that's why I think it's very, very important for you. And also, the second objective is understand how to apply these tools in finance. Okay, I already said about implementation, but how to use the, the idea here is not only use the way you do, but also how to use the same tools in other countries. Okay, so in that way, this course will be very, very powerful. Okay, what else we have here? Okay, I'm this is not the final grade, okay? The percentage can change. I will have the final percentage next week, I promise you, but you will have you will be evaluated in participation, okay? You will have midterm, final, and 3 assessments and 1 project, okay? Those are the items that Gonzalo and I will evaluate during the course. As I said, the percentages can change a little bit. I need to talk to Gonzalo to get the things done. But the 4 items will be evaluated during the course, okay? In participation, I will evaluate the things that we will doing during previous classes, okay? For example, it can be that on Friday, next Friday, I can give you a quiz about statistics and probability, some not difficult questions, okay? It's going to be like 10 minutes quiz for everyone, and I will grade you the same day, so you can keep a track of your grade while we are going through the course, okay? It can be also through some challenges. I have in the slide some examples and exercises, and I can ask you to solve those challenges and give me the answer. I can take that as also as participation, okay? Those challenges can be like mathematical things that you need to solve, or it can be also programming things, okay? That's why this course it will take like seriously the R programming. I know that some people here probably have never programming R, but it's not that difficult. Gonzalo and I will help you, and when you finish the course, you will be able to put R programming as one of the skills that you know and you have learned in at least an intermediate level, and that is also very good for your job search, okay? So don't worry about that. Yeah, and also those quizzes and questions won't be like, okay, next Friday and Saturday you will have a quiz. Those can be random. I will take those quizzes randomly, okay? So the idea is that you are prepared, that you finish the class, you go through the slides, and if you having understood something, you let me know, or let Gonzalo know that you need some explanations about the things that we have learned. So at so when the week finishes, you know 90% of the classes. Okay. Do you have any questions about participation? Hi guys. Thank you, Andres. Anyone else? Awesome. Wonderful. Then we have the midterm and the final. Okay. Those assessment will be like any other midterm or final that you have already taken in any other course. So I will give you the questions. I will post the questions during the 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 day of the examination. I will give you some time. Okay, the usual 2 hours to solve the examination, and you will, when the time's out, you will scan your answers. Okay, you can use your cell phone. It's not difficult at all now to use the cell phone to scan your exercises, your solutions in a sheet like this, and you then need to upload your solutions. So I'll be able to correct them. Okay, that is the idea for the midterm, final, and the assessments. And for the project, good questions. Nice. For that midterm, you don't need art. If I ask you something about art, will be like not difficult, but not something like program. I'm thinking about that. Okay, I will tell you about the experience in past semesters, and I think that will repeat. I don't think in midterm I will ask you about art programming. It will be like you need to solve some exercises about time series, about volatility modeling, about statistic and probability, and Monte Carlo. Okay, solve things, solve equations. Sorry, some concept. Okay, let's see. Random tasks are equivalent to 3 assessment that. No, participation is 15%. Participation is 15. Sorry, Fernando asks, random tasks are equivalent to 3 assessments that figure in the presentation. Participation is less than that, 15%. But also I said those numbers are not close. Yes, yes. Those random quizzes are part of the participation. Yeah, yeah. So maybe we will have like 10 quizzes and some random questions during the class. I can think about using those random questions as extra points for you. So I can help you with that. I don't know if you agree with that. Okay, so it's like we have quizzes and also like extra points. So I think that can help you to get more. The participation is it's going to be like a quiz with 2 questions or 3 questions at most, not difficult at all. It's just to know if you studied the previous lecture, if you solve the exercises in the recitation with Gonzalo. Okay, so we will give you like some problems or a problem set, and if you practice, I think you will be able to get all the points in the participation quizzes. Shouldn't be difficult because it will take like 10 to 15 minutes. It shouldn't take more than that. Okay, can be programming. It's like you will be in your computers, and I will ask you, okay, please give me what is the meaning of using this data. Take the compute the log returns, and also compute the mean and the standard deviation and post it. Difficult at all. Give me the fourth and third moments for those data points. It's only Monday. Usually it will be on Wednesday, okay? But we can swap some classes. That depends on our schedule with with Gonzalo. We will try to keep it like that. Wednesdays, the TA class, and Fridays and Saturday, my classes. Okay? Yeah, don't worry. I understood, Roy. Any other question? Great. Okay. This is the okay. Yes, I will do it on Wednesday. Okay. Just let me finish the percentages of the evaluation, and I will do it. And so we can go through the outline of the course. Okay. Good. Thank you, Stordo. Excellent. Okay, this is the outline of the course. Okay, we have 7 main topics. In the first one, we will review your knowledge about statistics and probability. I know that you have already learned those topics. I just need to like brush your knowledge, because we will use those statistics and probability tools for the rest of the course. Okay, it's like the expectation, the variance, what else? The probability function, there's cumulative probability function, okay, the joint probability function, independence, random variables, things like that. Okay. Then we will we will study Monte Carlo simulation. This tool is a very powerful tool, and we will use it throughout the course. Probably during this, I don't know if you are able to see. Okay, can you see the mouse arrow? I don't know. I don't think so, but okay. The sorry guys. In the risk term structure, okay, and in the in the advanced topic, you will use intensively Monte Carlo simulations. Okay, we will use also Monte Carlo. Okay, let me see. Oh, good. Okay, I was saying in this. Nice. Okay, in this multivariate volatility modeling. In this multivariate volatility model, we will use intensively Monte Carlo simulation. Okay, but we will use also Monte Carlo during this part, just to simulate some time series. Okay, to see, it's like doing our own experiment, like a control experiment in financial modeling. What, for example, what is the difference between the data that is used in engineering and the data that we use in finance and economics? Is that usually in engineering you can control your experiments. Okay, that is difficult in finance and economics because you see the realization of your financial data once. Okay, you only see one realization of inflation or returns of the S&P 500. But when you use Monte Carlo, we are able to like control the whole experiment. Okay, we are able to control the whole experiment, which is very difficult when we try to model a financial time series. Okay, because in the financial series you will see breaks, you will see change of regimes, and things like that. With Monte Carlo, we can control all of the things. Anyways, then we will study time series, like traditional time series, stationary time series, and non-stationary time series. Okay, unit root and stuff like that. Then it will come the most exciting part of the course, will be modeling volatility. In finance, this is one of the most important things that you have to learn, because the returns, the log returns, the daily returns of assets won't behave like normal as we usually assume in economics. Okay, the behavior is not normal. The return shows some where's this slide this week? Yes, like these weeks. Yeah, you see the prices of the assets in the fixed income market and in the in the market. Just give me a Okay. Yeah, and in the equity, we've uh, we've seen a lot of volatility, and the volatility usually like cluster. We will see volatility probably next week, and when everything goes to normality, also the evolution of time series will go to normality, and the volatility will go down. So things like that. That's why it's very, very important to understand how to model the volatility of the returns. That will be useful not only for let's say quantitative asset allocation, but also for risk management. Okay. Then later, so in the fourth part in volatility model, we will model the univariate volatility, univariate time series of returns. Later on, we will model simultaneous volatility. Okay. Finally, a fun part. We will model the risk term structure. What is this? You already know about the term structure of interest rates, right? Can anyone tell me what is the term structure of interest rates? Have you heard about that? Okay, kind of like that. Longer time, higher rate. Okay. Yes, yes. The term structure shows you uh, uh, the relationship between rates and the term. Okay, as Roy said in the chat, when the term is longer, you will see higher rate because there are some things that we call liquidity premium. Okay, if you want to get a loan for 30 years, yeah, market segmentation also, and also expectation. I will give you a very simple example. If you want to take a loan, if let's say a company wants to take a loan for 30 years in comparison with a loan overnight, probably the rate that the banks will charge to this company for a 30 years loan will be higher in normal times. Okay. Okay, this is what we see in terms of rates, but also we will see this kind of structure in the risk. Okay. So the idea of this part is how to model the risk over time. The risk for the next year, the risk for 1 week, for 2 weeks, and that is very useful for risk management because in risk management usually Basel asks banks to report these risk measure called value at risk for the next 10 days. Okay, and to compute this risk metric for the next 10 days, usually what banks do is compute the value at risk for the next day and multiply that value for the square root of 10. And that holds when you assume that the return is normal. But I have said before that the returns of the assets are not normal, so we need to find a way to estimate in a more precisely way these value at risk for the next 10 days. And for that, we will need to use Monte Carlo with the models that at that time already know. I mean, volatility and multivariate. And at the end of the course, hopefully we will get this part. I will teach you about how to get optimal portfolios using an extension of the framework that Markowitz gave us. Okay, there is a whole framework called portfolio optimization. Markowitz construct all this theory about portfolio optimization, but this framework is has some flaws. Okay, so the idea is complement this theory, this framework, with other tools that help us to overcome those flaws. Okay, and we will use also Monte Carlo to do that. So many of the things we will do throughout the course will be very practical. We will be using R. Okay, that is the one of the main ideas for this course. Okay, so you have any questions so far? So we can go. So we can jump to the lecture for today. This is the last slide. Yeah. Anyone else? Okay, good. Okay, excellent. So let's go through the slides for today. As I said before, today we will revise some of the basic concepts in statistics and probability. I know you already know this. Okay, so we will go through these slides, and if you have any question, just let me know. Okay. Okay, this is the content for this presentation. We will revise random variables, expectation, joint distribution, and we will end with estimation. Let's start with random variables. Okay. I usually ask about random variables during the first class, but I think when you already have the slides, it's like I spoiled the question. Okay, what do you think what is a random variable? Try not to see the next slide. I like when people intervene. Okay, take potential values from a distribution. So some the elements that are behind the random variable, take different values. There are some things that there is something that we call distribution, and the value take it takes is random. Oh, I think, are you able to see it when I share it here? Let me see. So you are not able to download it. Oh, okay, 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 okay. I will post it there. Let me see. Let me see. Content. Give me 1 second. Let me see. Lectures. Browse. Okay, so it is already posted. It is in content. Now you can download it. Okay, anyways, let's go through random variables. A random variable is basically a function, okay? It is basically a function. And okay, and we will study real value random variables. It's a function that that goes from something that we call sample space and goes to the real line, okay? And what is the sample space? The sample space is the space of all the outcomes of a random experiment. Probably when I said random experiment, something a bell rang in your heads. And a random experiment can be like tossing a coin, rolling a die. Okay, for example, if I toss a coin, that coin can have two outcomes, heads or tails. Then heads and tails are the elements of the sample space of this experiment. The experiment is tossing a coin. The the sample space will be head or tails. Okay, and a random variable is a function that goes from this sample space and goes to the real line. Okay, for example, in this slide, this example, okay, I have this random variable x that takes two values, 0 or 1. It takes the value of 1 if you get heads, and takes the value of 0 if you get tails. That is a random variable. Okay, just a function. There is other property that says that such that the pre-image of any interval in the real line is an event in the okay, and what is an event is just a set that we can measure through a probability function. Okay, anyways, it's just a function. Okay, a function that goes from sample space to real line, as this example, this random variable goes from the sample space that by flipping a coin and goes to these two values, 0 or 1, just like that. Okay, and for any random variable, okay, there is something that is associated, and is tightly associated, and we call it cumulative distribution function. Okay, any random variable has a cumulative distribution function. Okay, and the cumulative distribution function is defined as this: the cumulative distribution function, the capital F of x, capital X of x. This x is lower x, is equal to the probability that the random variable is less than this small x. Okay, that is the cumulative distribution function. Is the probability, measures the probability that the random variable takes values lower than a number. And this function has some properties. It shouldn't be negative. Okay, so it is always greater or equal than 0, and also it won't be greater than 1. So it should be bounded by 0 and 1 for any real value. Okay, that is the first property that has this cumulative distribution function. What else? This the cumulative distribution function is a non-decreasing. Okay, so let's put it this way: it's always a function, or but never it will decrease. Okay, and the third property is the following: if you compute this function, this random variable, when x goes to minus infinity, the value of this cumulative distribution will be 0. And if you take the cumulative distribution function of plus infinity, so when the x goes to the right, this cumulative distribution function will be 1. It's like let me see. Shapes. Okay. This. Okay. Okay. Black arrow is the y-x, and here's the axis, and this is the x-axis. Okay. Let me see. Let me see. This is so this is the value 0, and this is the value 1. So this is like 0. Okay. Let's see. A cumulative distribution function uh, is something like this. It shouldn't decrease, so this is like wrong, but it should be like this. When the x goes to when x goes to minus infinity, the distribution function goes to 0, and when x goes to plus infinity, the distribution function goes to 1. So it should be some kind of function like this, and these lines, the x equal to 0, actually it's y equal to 0 and y equal to 0 and y equal to 1. Those should be like the these this function won't touch those lines, but it will get closer and closer to those lines. Okay, let's go back to these slides. See? Okay, so that is the cumulative distribution function. Okay, so when we have a okay, so any random variable has a cumulative distribution function. Okay, the random variables can be of two types. They can be continuous or they can be discrete random variables. For example, a continuous discrete random variable can be, for example, the one that we saw in this slide here. Here in this slide, this random variable is a discrete random variable because it takes a finite number of values, just 0 or 1. When the number of values that a random variable can take is finite, we will say that the random variable is a discrete random variable. But when the random variable can take an infinitely number of values, we will call this random variable a continuous random variable. Okay, so here in this expression, I have on the left side of the identity the CDF, the cumulative distribution function, and on the right we have an integral, that goes from minus infinity to x. This x is the same one that this one. Okay, so the cumulative distribution function, or CDF, can be computed as the integral of this function, this f, small f. This small f, we call it probability density function. Okay. Just give me a second, okay? Sorry, guys. So On the right hand side, we have this integral of this function. This function we call density function, okay, or probability density function. Not all the random variables have density function, okay, but for our purposes, many of the random variables that we will study will have density function. So the integral of a density function up to one number is going to be the cumulative distribution function of that number, okay? So what happens when I integrate this function throughout the real line? I will get 1, okay? That is because of this, just this, because of this, sorry, because of this property, okay? For example, I have here this random variable that is called a uniform random variable. Have you heard about about the uniform random variable? Do you know what is the density function of this uniform random variable? Okay, good. It's 1 over b minus a. In my example, what is the value of b and what is the value of a? Good. So in this case, this the uniform random variable, the standard uniform random variable, have a density function that is 1. Okay. Let's see. When x is between 0 and 1 and 0 otherwise. Good. So we have here an example of density function. Okay. What is the density function for the standard normal random variable? The normal random variable is one of the most famous and used random variables. So I think you should know what is the density function of this random variable, at least the standard normal random variable. The standard one has a mean 0 and standard deviation or variance equal to 1. So with those parameters, what is the density function of a standard normal random variable? I will go to the is like this. See, I'm not very good. Yeah, it has a bell shape. It's like this. Okay, good. There is x mu sigma. Okay, let's say there is mu. Okay, is the mean. So there is sigma, which is the standard deviation. Okay, I will call it. It's like this, right? This is the standard deviation. Okay. And it has this Okay, it has this shape. Okay. Alright, I will get proficient in the next couple of weeks doing this. Okay, pencil should be like this. Right, and the function is 1 over a square root of 2 pi. I would just the standard, okay? 2 pi exponential of x squared over 2, and it should be like minus here. So this is the density function of the standard normal random variable. Okay, Roy said, okay, x minus mu sigma. Yes, that is the case when you have mean and variance. In that case, the normal random variable will be like this: square root of 2 pi, okay, sigma square exponential of minus, here you open parentheses, x minus mu, sorry, there is not a square here, a square over 2 sigma square. Okay, so this is the density function of the normal random variable. This is for the standard with mean 0 and variance 1, and this is for the normal where mu and sigma are the mean and the standard deviation respectively. Okay, let's go back to the, and this okay, P stands for the actual P. Yes, 3.14, 59, 26, blah blah blah. That is pi. Okay, let's go back to okay, so now let's go through the next slide. Now we have the expectation. Basically, the expectation is just a weighted average. Okay, let's put it that way. It's a weighted average, as we can see here in the slides. Okay, can you see the rectangle? Okay, okay, good. So the expectation of a random variable, any random variable has an expectation. Okay, the expectation is defined as when the random is continuous as an integral. The integral of that random variable that I'm putting here inside the brackets. Okay, so let's see. The notation here is E stands for expectation. Okay, the expectation. X, capital X is my random variable, as it says here. So the expectation of this X random variable is defined as the integral of X multiplied by the density function. and this integral should be taken throughout the real line. Okay. When you see this integral, it's not like very handy to understand the idea of expression. But when we go to the discrete case, when we have a discrete random variable, the expectation can be seen as a summation, as a sum of x multiplied by the probability that the random variable x, capital X, takes the value of x, small x. Okay, so here you can see that the expectation can be think as weighted average. Okay, it's just a weighted average. Here the weighted average is just taken continuously, but you can think of the integral as a sum. Okay, that's how you define the integral. That's how the integral is defined, as a sum, as a summation. Okay, good. The PF, okay, for the continuous case, we call this f, lower f, the probability density function. Okay, but for the discrete case, we won't usually call it probability density function. We call it probability mass function. Okay, I will probability mass function. Yeah, that's correct. Probability mass function. It's just a name, but it's the same. Okay. Any other question? Okay, let's go to the next slide. Some properties of expectation. The expectation is, okay, let's say we have two random variables, x, capital X, or upper X, and capital Y, two random variables. Those can be continuous random variables or discrete random variables. And let C be a real number, okay? Any real number. Okay, the expectation of the sum of two random variables is the same than the expectation of the first random variable plus the expectation of the second random variable. So the expectation of the sum is the sum of expectations. And if I take the expectation of a constant multiplied by a random variable, that will be the same that that same constant multiplied by the expectation of the random variable. It's like you can take out this constant from the operator called expectation. Okay, take it out and just take the expectation of x. And other property is the following: if x is a non-negative random variable, so it's a random variable that takes only positive or zero values, the expectation won't be negative as well. Okay, so I have one exercise here. So when I said during the logistic part of this lecture, we will see some challenges and exercises in the slides. I was talking about these kind of things, for example. Okay, this can be like the extra points or part of the things that I can evaluate during the participation. Okay, not for today, of course. this first lecture. So this is like our simulation. So we have this exercise. X and Y are random variables. We know the expectations. Let's compute. Good. Awesome. Excellent. Excellent. That's the idea. So I will put it probably in, we have some pooling or something like that. But that is the idea. Thank you. Good. Then the random variables. Okay, we know what is a random variable. We know that random variables have also a cumulative distribution function, or a CDF. And if the random variable is a continuous random variable, it can have something that we call probability density function. And if this random variable is a discrete random variable, it will have something that we call probability mass function, but it's the same. Also, we have learned that the random variables have expectation, okay? And we know how to compute expectation. It's just an integral, okay? Or if we want to get intuition about expectation, it's just a weighted average of the values that this random variable can take, multiplied by the probability of that variable takes those values. But also random variables have moments, okay? The moment of a random variable is defined just an expectation, okay? See, the moment of a random variable is defined as an expectation. Okay, so the first thing of a random variable is when m takes the value of 1. So when m takes the value of 1, that is the first moment of a random variable, which is also the expectation of the random variable. We know that. But then we can have the second, the third, the fourth, so on and so forth, moments of this random variable. Okay? You know what is the second moment of a random variable? Can you give me the name of the second moment of random variable of you had? Okay, it's called variance only when the mean is 0. Okay, because the variance no is the second moment always. The variance is something that we call, see, is a central moment. Okay. Yes. As you said, Fernando, the variance is a deviation, okay, from the mean. That's why variance will be the second central moment of x. But what happens when mu, the mean, is 0? Variance will coincide with the second moment of the random variable. Okay, just some tricky thing, but the variance is the second central moment. Okay. Okay. Let's say what it says. Okay, this is measured by its mean, and we know what is the value. Okay, here the dispersion of the distribution of the random variable is measured by the variance, and that is the second central moment, as it says here. we usually use the notation to compute the variance. Should here, instead of lower x, should be capital X, okay? Change here, there is a typo here, should be capital X. The variance, usually we denote the variance using this Greek letter sigma square. That is the variance. And also we know the square root of the variance, sigma, is called the standard deviation of the random variable. Then we have something that we call, for example, skewness and kurtosis. Those measures are related to central moments of a random variable. The skewness, okay, the skewness is related to which central moment? The third. Good. And the kurtosis? Good. Awesome. Fourth. The fourth central moment. Okay. It's related because it's not the third and the fourth central moments, because we need to scale those moments to get the skewness and the kurtosis. Let's go through. Okay, here. The skewness, which measures the asymmetry of the distribution, is computed as the third central moment scaled by the cube of the standard deviation. So we use this deviation to scale the central moment. And the kurtosis, which measures the tail heaviness of the distribution, as the fourth central moment scaled by the power 4 of the standard deviation, or if you want, this is the square of the variance. Okay. One important property about the fourth moment is this one. The normal distribution has a kurtosis of 3, okay, and skewness of 0. If the skewness is 0, that means that the distribution is symmetric with respect to the median. Okay, is symmetric. Okay, and the normal distribution also has this kurtosis of 3. For example, when there is something else. Have you tried to compute the kurtosis in Excel? Do you have an Excel spreadsheet open? Can you compute the kurtosis and tell me what you get when you compute the kurtosis? Or if you have heard about that before, of normal random data. Let's say you compute normal random data and you try to get the kurtosis or any other data. But for normal data, for data simulated using normal distribution, you will get a different number. Probably you will get 0. And that's yes, 0. Why 0? And if you see that, probably the next lecture you will come and argue to me and say, okay, Jesus, I don't get why you said that normal distribution has a kurtosis of 3 because Excel gave me 0. And the thing is that when you try to compute the kurtosis, sometimes what you get in some programs like Excel, for example, as I remember, is something that we call excess kurtosis. Okay, and the excess kurtosis is just the kurtosis minus 3. Okay, it's like trying to scale the kurtosis using the normal kurtosis. That is like kurtosis minus 3. That is the excess kurtosis. So don't get confused about that. Okay. Now let's go back to okay. One more thing here. Okay, we have talked about the moments, the random variables. Random variables have moments, have central moments, but also random variables have something that we call moment generating function. Okay, and probably when you have to study some of your courses, you have used the normal distribution. And because or why using normal distribution? Why people use normal distribution to teach things? Because normal distribution is very easy to we call it in math characterize the random variable just with two parameters, the mean and the variance. You don't need any more information to characterize a random variable that is normal than the mean and the variance. If you have the mean and the variance, you can know everything about that random variable. You can compute probabilities, percentiles, whatever you want. That's why the normal distribution is very, very useful. Okay? So the idea is, how can I approximate most the distribution of a random variable? If you know the distribution of a random variable, you know everything about that random variable. Okay, so one way of characterizing completely a random variable is using something that we call moment generating function. And the moment generating function of a random variable is defined as this. Here m of x of t is a variable, not a random variable, it's just a variable, could be anything. The random variable here is x is a random variable, t is a real number, and we call this the moment generating function. The moment generating function of x is defined as the expectation, and we know how to compute the expectation of the exponential of t multiplied by x, where this x here okay is this x. That is how we define the moment generating function. Why is very useful the moment generating function? It's useful in this way. Let's say you have two random variables, okay? X, okay, have y and C. Those are two random variables. And those are two random variables. And let's say you know what is what are the moment generating function of this random variable and this random variable. But you don't know what is okay. For y, you know the moment generating function and the distribution function. Okay, so let's say you have here for y, you have the CDF. Okay. Here is C, you don't know, I don't know the CDF. Okay, you know the CDF for Y, you don't know the CDF for Z, but you know the moment generating function for these two random variables. Luckily, the moment generating function for both random variables is the same. Let's say it's the same. Okay, if the moment generating function for this random variable y is the same, that is the same that the moment generating function for z, then you can say that the CDF that you don't know for this random variable should be the same than this CDF, that the CDF of y. Why? Because both random variables share the same moment generating function. So if you have two random variables that share the same moment generating function, then the same random variables should have the same CDF. That's why the moment generating function is very, very powerful. Okay. So I have here one exercise. You have to do it at home. It's like homework. Okay, sorry. Only apply CDF. Yes, because at the end of the day, the CDF characterizes completely the random variable. So I can say anything about a random variable if I know what is the CDF of this random variable. That's why it's very important, very powerful, this like theorem, okay? Because I said this property. If two variables share the same moment generating function, then the conclusion will be both random variables have the same CDF. If you didn't know that the CDF of one of those random variables, now you know it. Just because they share the same moment generating function. Yeah. Okay. Let's go to the next slide. Okay. Here's some properties. I think we won't use this. Okay, let's go to the now. Okay, we have studied random variables. Now we need to study something that we call multivariate random variables. Okay, multivariate random variables. Okay, before we continue, do you have any questions so far about random variables, station, central moments, moment generating function, some properties about the expectation? Any question? Something that you you need to you need some clarification? Okay, good. Excellent, excellent. Okay, let's go to the. Thank you, Fernando. Okay, let's go to why the second moment always be. Okay. As I said before, the second moment. Let me see. The second moment, the expectation of x squared. However, the variance is the expectation of x minus the mean all square. That is the variance. When m here is 2, mu is the mean, the first moment, if you want. See, yeah. The central moment is always the variance. The second moment will be the variance only when mu is 0. Got it? Yeah. As you said, Roberto. As you said. Excellent. Anything else? Uh, yes, Mauricio. I have elaborated this presentation with just the necessary theoretical things that you need. Okay, no more or less than that. Because I don't want you to spend time doing things that you won't use throughout the course. I just need that you learn or review and remember things that you will use it. And I'm sure this is my fourth time teaching this course, and it's always the same. We use everything in these slides throughout the course. Okay. Good. I like the dog in the profile picture. Anyways, let's go to the multivariate case. In the multivariate, we have two random variables that in some way are related. Let's say we have two random variables, and these random variables can have something that we call joint CDF, the joint cumulative distribution function. And this joint cumulative distribution function will be defined in the same way that we already defined cumulative distribution function. If you remember, in the univariate case, the cumulative distribution function, we didn't use y here and this one, okay? So let's see. If I in the univariate case, we have something like this. X probability of capital X less than small x. This is the universal case. Okay. In the case, the joint CDF of two random variables is, you can see the analogy between those definitions. Add this new random variable here, this small y here, and this is what we call the joint CDF. And as before, we had in the univariate case the probability density function. Very similar in the multivariate case, probability density function, and the probability density function will be this small f function. And to get the probability density function to the CDF, the cumulative density function, you have to integral from minus infinity up to this small x and up to this small y of the density function. Okay, when you have two random variables, you need two integrals. You have three random variables. How many integrals you will have? Yes, three. Okay, good. And there is something else that we haven't seen in the univariate case, something that we call the marginal distribution and the marginal density. Okay, the marginal distribution is the is defined as the integral, okay, double integral of this density function. But if I want to compute the